Okay, so let's continue. Right, so we have to draw a network. We have given 6 vertices, and then we have a number of edges. So let's draw them. A, B. So A is connected to B. A is connected to Y. A connected to B connected to X. B connected to Y. C connected to X. C connected to Z. X connected to Z. X connected to Z. And Y connected to Z. Okay.
Doctor, I think the screen is not shared.
Okay. Thank you. Right. Can you see now? So thank you. Thank you for informing me that. Otherwise, I would have not shared at all. Right. So this is how the network looks like. Maybe you can draw, I mean, more beautiful than this, but this is how the network looks like, right? As you can see, the highest degree being 3. X has the X, B, and Y has the highest degree, right? So the highest degree we denote as the delta. Now let's say this is the network H, so delta H is actually 3. Oh, again, those having highest degree would be of X from B and Y, right? And then for the lowest degree would be 2. Or maybe I draw a different shape. A, C, or even Z having 3. So, and then minimum, yeah, the lowest degree would be 2 is for A and C. Oops. C. Okay. Now, so basically that is the route, yeah, for this flight. Okay. Of course, there are many other things can be done, which we will be looking into for the next lectures. Anyway, that's the answer. Let's move on. Right, so now we come to a question, right? Why represent problems or situations with a network? The answer would be many optimization problems have a special structure which allows for them to be modeled or solved as networks, right? When it comes to data science especially, so a lot of problems, the data is so huge, it is really hard to visualize one thing. The next thing is, of course, hard to analyze. Right, so we represent them in the form of a network, and then, of course, we can visualize. The next thing to do it would be to analyze them. There are many algorithms which can efficiently analyze these networks. Okay, so the purpose would be, of course, efficient data processing. Right, so we would be able to represent the network in a very simple matrix, actually, in which we will look into it in a while. For example, a simple problem will be path finding. If you see, for example, here, if you see like how would I reach to, I want to take flight from A, I want to reach to Z. So there are probably a number of ways to do it, right? One way would be to, I can fly transit to Y and then go to Z, or I transit to B. Or again, if I have transit to B, then I go to Y again and to go to Z, right? Is there any other option? Probably no, right? Or maybe if I have ample of time, probably I've got nothing to do in life, I would go A to B, B to A to B, B to X, X to C, C to Z. Maybe I want to go to all the cities around here, right? So I might be missing Y. But anyway, these are the things that can be done. Yeah, simple path finding. Right, and then visualization, of course. So, but rather than looking at how they are connected in a table form or in a different form, this by looking at this graph, we will be able to visualize easily how they are connected. Okay. Okay, so that is the actually motivation of representing problems or situation with a network. Okay. Now, storing network in a computer, right? Basically, many ways. Probably one of the best way will be to use a matrix. Okay, this matrix is called agency matrix. Agent means next to each other, right? So agency matrix is a matrix which denote the edges of the vertices, how they are connected, right? Okay, so how we do it? Excuse me. So assume we have n vertices. So the our agency matrix would be in the form of n times n. It's a square matrix. So where Aij, yeah, the Aij represents the number of connection. For example, if Königsberg Bridge, the number of bridges, right? So usually we denote this matrix, adjacency matrix, as M or A, yeah, usually A or M, right? So that the entries, yeah, the entries are the number of edges, can be number of edges, can be even, can be anything actually, but here the simplest form would be number of edges. Right? Let's look at number of edges first before we go into other ways to represent this entry. Yeah, previous example again, I take Königsberg problem, right? So we have A, B, C, and D, right? So basically the row, yeah, the row and column. So this is row. Yeah, so this is the row for A, basically. And then of course, this is a column for A, right? So A is connected to B with 2 bridges. A is connected to C with 1 bridge. Yeah, C is connected to B, 2 bridges, 1, 2. A to C is 1 bridge. A to D, there's no bridge between A and D, so it's 0. The entry is 0. Right? Similarly, we can do for B. So B is connected to A, of course, 2 bridges. B is, of course, not connected to B. B is connected to C with 1 bridge. Yeah, this is a bridge. And then B is connected to D with 2 bridges. Okay, so we can just move on, enter the entry for each, and then we are done. So this would be the adjacency matrix representing Königsberg's bridge problem. Okay, so this is how we store the graph information in the computer. And then when we want to visualize this graph, the entry would the input would be the matrix, the output would be the graph. Okay, so there are many software can be used to draw this graph. The input will be as simple as the matrix, adjacency matrix. Okay. So draw a network from given adjacency matrix. So you can try, right? Again, so denote, first denote. So we have, I've given you a notation here. So V1, V2, V3, V4 represents the vertices. So V1, V2, V3, V4. Of course, the row is the same thing. Okay, so we can, you can like, okay, there are 4. You can start drawing V1, V2, V3, V4. Remember, anywhere the point is coordinate free, you can put anywhere you like, as long as the edges is stay intact. So for example, V1 is not connected to V1, right? And then V1 is connected to V2. There are actually two bridges connecting V1 and V2. Maybe change the color. Okay, so 2. And then V1 to V3, no. V1 to V4, there's 1. V1 to V4, there's 1. V2 to V1. In fact, the trick would be, if it is, you see, you can see that it's somewhat symmetry, right? So 2, right, symmetry, isn't it? So 2. So you can just look at one part. It's sufficient enough to draw the whole network. So we have done this, and this yet to be done. V2 to V3. There's 1. V2 to V3. Right? V2, V3, so done. Then V2 to V4, none. V3 to V4. V3 to V4. V3 to V4, we have 3. 1, 2, 3. Okay. So this is how the network looks like. Of course, you may draw in a different way, right? If it is not symmetric, then of course you have to go below and start drawing, right? Example of not being symmetric would be like, for example, let's add here 2. Let's say this is 2. So if we have 2 here, V1 to V4, V1 to V4, we have 2, right? So if 2, then if I draw like that, then of course this becomes 2, 2, right? So it's still symmetry, which means in order to violate the symmetry, we need to create a loop, right? That's just telling you like when the matrix will not be symmetry, and there is a loop. A loop would be, example, like that. So V2 to itself, for example, now V2 to itself, this is 0, right? So now we will change it to, let's say, 1 if there is a loop, okay? So this is how we draw from given a matrix into a network, right? Okay, so a different way of drawing. Yeah, previously I drew like that. The original answer is okay. So it's the same thing here. Okay. All right. So weighted network. Well, okay. So first is the definition. A connected network G is called a weighted network if each edge E in G is assigned a positive number W, which is the weight, called the weight of E. Okay, so this is an example. You can see this is an example of a network, of a weighted network. So rather than, if it is not written, usually we assume is 1. If it is given a weight as such, for example, 7, which means B to E has a weightage of 7. So what is 7? 7 can represent anything, right? 7, for example, can represent distance, time consumed. If let's say if it's a road network, B is connected to E, maybe the amount of time taken to travel from B to E, or a distance can be 7 kilometer, or cost, maybe 7 ringgit, yeah, or capacity, maybe 7 passengers, anything for that matter, right? So that is the purpose of weight. So we impose weight for each edge as such to represent something, a quantity of interest, distance, time, cost, or capacity. So by doing so, we would be able to do routing optimization problem. We would be able to solve it using various kind of algorithm that we will soon look into. Okay, so there's another type of graph which we would be using. Okay, it's called a directed network. In the mathematical notation, we call it as a directed graph, which is similar to a directed network. What is a directed network? A directed network consists of a non-empty finite set or vertex set together with a set, edge set, of an ordered pair of distinct elements of the vertex set. So here the keyword is ordered pair. So previously AB, previously from A to B, we represented in a tuple, two tuple like that, A to B, right? In fact, the does not matter, right? If there is no direction, then the order does not matter. It can be, I can also write B to A, right? Sorry, B to A. Order does not matter for a network with no direction. Whereas the network with the direction, usually we call it as an arc rather than calling it as an edge. We call it as an arc to differentiate between network with direction and network without a direction. And this time around, a two tuple, the right way of representing it would be a two tuple AB. So AB, just like a coordinate system, AB, the order AB is not the same as BA, right? So using a two tuple. So now this is the direction. A, starting from A, it goes to B. Okay, so the network consists of directed arcs. Is called a directed network. So pretty much straightforward. Yeah. Okay, example of a directed network. Right. So usually, for example of a problem would be traveling salesman problem, which we would look into in maybe in 2 weeks or so. Right. So a salesman got to go to a number of places, for example, city A, B, C, and D, so in which there is a direction, how he's going to travel, from where he's going to start, where he's going to end. In any case, is he going to travel once for each city, or he's going to travel twice for each city, depending on how the cities are connected, and also the distance of each city, right? So we need a direction for this network, such a way that you would be able to follow in sequence. Okay. All right. So of course, in a directed network, we would be able to get the degrees information, the degrees information for each vertex, right? For example, the in degree. Now we have in degree and out degree. For a standard network without a direction, there's just one degree, right? Whereas for a network with direction, we have in degree and out degree, right? For example, let's take A. So A has one out degree in which we write it with the negative sign of superscript D representing degree of superscript minus representing out degree, and of course in the bracket represents the vertex that we are looking into. So this one, whereas the out degree of A would be oh, I got it the other way around actually. Incident into actually into. This is incorrect. Sorry. Let me correct this. Oops. Okay, there's a typo here. Please take note. So out into node I. The in degree of node I is a number of arcs that are incident into node I. So into node I, this is into node I, this is into node I. So into node I, yeah, is 2. Yeah, there's a typo there. The out degree is incident out of node I, which is going out as 1. Okay, please take note. There's a typo. I'll correct it and I'll post it tomorrow. Right? And if the in degree and out degree for node I is similar, then we have a symmetric matrix. Yeah, in fact, we can easily visualize if we represent this graph or network in a matrix. Okay, the directed network metric if we have in node in degree and out degree not similar, right? So in this case, 2 of course not equals to 1, so we have asymmetric network, right? Okay. There are a number of definitions that I would like you all to know before, I think, before we end this today's lesson. First is path. A path is a sequence of distinct edges connecting node P to Q. Let's look at here. So a path can be, yeah, for example, A, B. This is the first edge. We start. Let's say we start from A, okay, and then B, C, and then C, D. So this can be a path, okay. So a sequence of distinct edges connecting nodes P to Q. So just now we were connecting A to D, right? A to B, B to C, C to D. In fact, I can go back to A, right? If I were to go back to A, then I'll take path D to A. This is also a path. Now, next is a directed path. What we did just now is in fact a directed path. Why? Because the network is a directed network. So the definition would be a path with distinct directed arcs from node P to node Q is a directed path. Okay, so just now what we did is actually directed path. Why? Because the network has a direction. A cycle, or we also call it a circuit, is a path that starts and ends at the same node. So in fact, this path that we have written below is in fact also a cycle. A directed cycle, yeah. To be specific, it would be a directed cycle. Why? We have direction. A connected network is a network where all pairs of nodes are connected by a path. This is a connected network. This is in fact is a connected network because why? All the vertices. I can reach to any of the vertex in here by starting at a point. For example, let's say C. I can reach to C by taking some sort of like a path around in this network, right? So it is a connected network. Whereas in this exercise, if in this exercise you will see W is actually a singleton. We call it as a singleton because it has no edge connecting to any other vertices. So if I were to reach to W from any other vertex, it would be impossible because why? It is a singleton. So this is a disconnected network, right? In fact, this network has two components. One is W, and the other component would be the rest of the networks and the rest of vertices connected, right? As you can see. Similarly, in the previous example here, in a friendship network, if you look at a friendship network, this friendship network is also a disconnected network. Yeah. Why? Of course, this is by itself. There's one connected component, we call it. This is another connected component. There are actually two connected components in here. Rather than being a connected network, there are two connected components, not a one connected network, right? Okay. All right, so that would be, I think that would be the end of our lecture today. So go back and try to do the simple exercise. And then just to give you a heads up, remember there will be assignment 2. So I will give assignment 2 in week 11. All right, so currently I'm expecting to give a problem on shortest path problem and also minimum spanning tree. Whereas for quiz, there'll be also a quiz. So I intend to do a quiz in week 15 when I see you face to face. So probably we can do quiz on traveling salesman problem or network flow, right? So all this assignment and quiz, of course, it contributes to your career mark. At the same time, it prepares you for your final exam, so that you do more exercise such a way that in final exam you know inside out, there will not be any doubts. You'll be able to answer as perfect as possible. All right. So the takeaway for today's lecture would be, of course, networks. Right? Networks are highly visual. Easily we can identify relationships, or we can easily find paths, and etc. Right? And then, of course, efficient solution procedures. Right. So in the lectures to come, you would see how we can use algorithm to solve optimization problems for these networks. Right. So with that, I would like to end our lecture today. If you have any questions, please feel free to ask now.